Hey everybody. So make sure we're taking notes on what we're doing today. Our next day, we're going to be maybe looking at some demos of some of these gas laws and some of the gas things that we're going to be looking at today. For the most part today, we're going to be looking at jotting a few things down about gases. We're getting into gases and gas laws at the moment. Again, sorry I can't be here today. Make sure for the video to pause as often as you need to and make sure this stuff is in your notebook, okay? We're not going to get too far today into gas stuff, and we're not really focusing on the math for gases. We're kind of just focusing on the concept. So thinking about what gases do when you change certain variables. And the thing is, you've all dealt with this stuff before, maybe not in school per se, but in life you have. And so I usually like to bring up certain real life applications or real life examples of these two laws we're getting into today. So to start, we're going to define three terms that deal with pretty much everything, but we're going to focus on gases: pressure, volume, and temperature. All right. I got them colored here because I'm going to use these colors in all of my notes for pressure, volume, and temperature with gases. So I want to start with pressure. So I usually like to ask, okay, how do you put pressure on something? You kind of push it. Okay, so the more pressure you put on something, the more force you exert on something. All right. The definition here is it's the force exerted over an area. So if you think about how you can walk on snow, use snowshoes, because snowshoes have they're gigantic. All right, they're really big. If you put those on, all of your weight gets distributed very well. It gets distributed over the entire surface of the snowshoe, so you can actually walk on snow because there's low pressure. Take the snowshoes off, put your boots on, you just kind of go straight through the snow because you weigh the same, but all that force is exerted on a smaller area. So with gases, I like to think about gas particles just constantly hitting everything. Okay. Also a boxing match, bam, 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 bam. Harder that gas particles push against something, the more pressure there is. All right. So think about temperature. When you heat something up, gas particles move faster, so they hit more. If something is slower, if something's a lower temperature, they're not hitting as fast or as strongly, so there's lower pressure. So that's pressure in general. Volume we've dealt with before. It's how much space matter takes up. If you blow up a balloon, the bigger the balloon is, the more volume in the balloon. The smaller the balloon, the less volume in the balloon. Okay? And then temperature we've dealt with before. It's pretty much how fast particles move. So the faster particles move, the higher the temperature, the hotter something is. The slower the particles move, the lower the temperature. It's all about how fast particles move. So the average kinetic energy. Kinetic energy is the energy of movement, energy of motion. So the more motion there is, the higher the temperature. All right. So hopefully we have those down. If you don't have them down yet, make sure you pause it. What we're getting into today are two distinct gas laws and then what they do is they pretty much focus on how gases behave in certain environments. So make sure that we are pausing the video each time to get some of this stuff in your notes, all right? We'll go over a little more at a later date. We're going to do two laws. One of them is called Boyle's Law. This guy's name is Robert Boyle, so Bob's Law, Boyle's Law, you can call it. This one deals with something called a piston. You don't know what a piston is? It's just a little device that pushes gas in and allows it to expand. Pushes gas in, allows it to expand. Kind of like a syringe, you could think. So what I want us to do is draw this in your notebook. All right. And I'm going to erase this little box here. We're going to draw the piston at the beginning and the piston at the end. But again, take a few minutes and pause the video to make sure you're drawing this stuff out. Little dots I have here are gas particles. To make sure we're drawing those dots, and what I like to focus on is how the little gas particles are in relation to each other each time we're changing the piston. So in the beginning, I think we have, what, 10 gas particles, if I can count. I'm really tired. I think, yeah, there's 10. Okay, I can count. All right. So they're just kind of here doing their thing. They're just chilling. What we're noticing is that when you shove the piston down, when you make sure the gas is smaller, look at how these gas particles are aligned now. All right. I usually like to ask, are they closer or are they further apart? Well, they're much closer. Okay. Much closer. So if they're much closer, that means they're hitting each other more often. I like to think about this as, let's say that you have 10 people. Look at this picture, 10 people living in a house. All of a sudden, you cram those same 10 people into a much smaller place. Well, they're going to hit each other more often. They're going to they're going to into each other more often. Okay, if they keep walking and bouncing off the walls, they're going to hit each other more often because it's a smaller place. So this is Boyle's law. What's happening now? Don't really worry about the numbers here, but I'm just showing them for examples. If you were to decrease the volume of a gas, you have a trapped gas in something, and you decrease the volume. So in my numbers, I'm going from 4 liters to 1. See what the pressure is doing? The pressure is actually going up from 1 to 4. Don't worry about the values and the numbers. I'm just using them as examples here. But gases do this, and in real life, this happens too. Imagine like all the people. So imagine Soldier Field, okay, where the Bears play football. Imagine if that stadium is packed, but then all of a sudden, all those people have to like go into a smaller arena. It's going to be jammed, and they're going to be all like, "Oh, get me out of here." So that's just how it works. Okay. So same thing here. 10 gas particles. There's more than 10 usually, but always. Just for this example, there's 10. Shove them into a smaller space, and they exert more pressure. So they're more like eager to get out. All right. And if you were to go back, they would the gas expands and the pressure goes back down. So make sure that we are writing this down as well. This is Boyle's law. The definition is right here. I got a little graph here as well. So make sure, again, you pause it and jot this down. Temperature is constant. So constant means it's not changing. Pressure and volume, I got P and V here. They're inversely related. So in math class, you may have talked about inverse and direct relationships. Inverse just means it's opposite. Okay. So as one value increases, in this case, if volume were to go up, pressure's like, I'm going down. The same with volume going down and pressure going up. It's kind of like a seesaw. Okay, in a seesaw, if one side goes up, this side goes down. My little calculator here. So if there's a seesaw, if this side goes up, this side goes down. Okay, you can't have a calculator where both sides go up. That doesn't break my $150 calculator. That's no good. That's an inverse relationship. All right, it's an opposite effect. So in my graph, I've got an opposite effect going on. So if you check down here, as volume goes up, as it increases to the right, check pressure going down. And the opposite is true as well. We'll get into these graphs a little more later, but all we got to know is that if volume were to increase, then pressure goes down. If volume were to decrease, like in the piston, pressure goes up. Okay. Again, make sure you pause. Make sure you get that on there. But one more gas law I want to look at is a gas law called Charles's law. And again, make sure we're pausing so we can draw our pictures and all that. This one I think is more applicable. This one you may have dealt with before. I see this all the time, especially in Illinois with the changing temperatures. I like having water bottles in my car. And a lot of times, especially this last week, like it was freezing like over the weekend. Then this week's actually kind of nice. It's like in the 60 degrees. So if you have a water or like a sealed bottle of water in your car, like a plastic bottle of water in your car, and there's a lot of air in it, a lot of gas in it. When it gets cold, you'll see that the bottle crinkles and changes. But when it gets warmer, the bottle expands and gets a little bigger. You'll hear it crinkle and you'll hear it expand. It's kind of interesting. Same with a bag of chips. If it's in the car and it's sealed up and it's cold and it's hot and it's cold and it's hot, you'll actually see and hear the bag expand and contract, expand and contract. So I usually deal with this as the balloon law, I guess, Charles's law. So I'm going to get rid of this little box here. Let's draw a balloon when it's hot. So the happy sun. Can you imagine if you saw up at the sun and saw it smiling? That'd be scary. I'd be terrified. So we got a happy sun here with a balloon. I'm going to call it 4 liters. But again, the numbers don't matter here. We're looking at the concepts, just seeing what things change. We got a balloon. It's a certain size. Say it's big, whatever. If you were to take this balloon and bring it into like a frigid environment, somewhere like Antarctica or Alaska or Siberia or anywhere that's freezing cold, or polar vortex 2 years ago in Illinois, whenever that was 2 years ago, yeah. Balloon shrinks. Okay. The reason this happens is because the balloon can expand. Okay, the volume of the balloon can change, and the reason it can change is because it's made of material that can change. But the temperature of a cold environment is much lower, so particles move slower. If you look at the picture, they actually get closer together. I like to think of this even when if you're outside and it's cold out and there's a bunch of people around and you know each other, like before COVID, everyone would get together to warm up because more people together makes things warmer. If you're outside and it's cold out, if it's warmer, you don't. It's warmer outside. You don't want to do that because it's too hot. So then you kind of spread out a little bit. So if you have a balloon in your house, put it in the freezer and it will get smaller because of Charles's law. So I just got rid of this little box here. Again, don't worry about the numbers. We're just looking at the concepts here. What we're seeing is that as temperature goes down, volume goes down of a balloon, like that. The last little thing here, then I'm gonna stop the video. Again, make sure that you're jotting this down and make sure that you are pausing the video so you can get this in. Charles' law states that pressure is, so when there's constant pressure, I usually deal with basically containers that can expand pretty easily. Things like car tires, balloons, bags of chips, stuff like that. Volume and temperature are directly related. Direct means that they kind of follow each other. It's like a shadow relationship. Okay. If you have a younger sibling, usually the younger sibling wants to do what the older sibling does. The older sibling is like went out to, do something. This younger sibling's like, oh, I want to do that too. And the younger sibling follows you around and you're like, oh, maybe you like it, maybe you don't. I don't know. It's a direct relationship. So as T increases, volume does the same thing. It follows, it's like a shadow. Can't stop it, it's gonna happen. And the same thing the opposite way. E goes down, volume decreases as well. And so this is an easier graph to look at. So basically it's a nice positive sloped line. So T goes up, V goes up as well. Same as it goes down. So if T goes down to the left, you can see volume follows it by going down. So we got the direct relationship. So we'll get more into this a little later. Make sure that you've answered the discussion post on PowerSchool today. It's underneath this video. Make sure you pause the video, obviously, to get some of this stuff down. Make sure you fill out the discussion post, submit that as proof of participation and stuff today, and follow the agenda for today. Thanks, everybody. Have a good day.